Uh, Anurag, can you speak once, just a little bit?
Can you hear me now?
Yeah, it
Okay, good,
works.
great, great.
Okay, so hello everyone. So I'm Tathagato from Amygdala AI, and it's my quite pleasure to invite Mr. Anurag Singh to do a presentation on his research. So Anurag Singh is a young enthusiastic researcher in TUM over here in Germany, and he has a lot of papers in uh, places like CVPR, ECCV, and many other prestigious conferences and top journals like IEEE Transactions and all. And his work mostly related to some advanced computer vision that he'll be talking about today. I don't want to introduce this topic, let him do that. But overall, he's a very good researcher, and he also got some honorable mention in NUS Singapore. So hope you will enjoy his talk. So Anurag, it's up to you. You can start with your presentation.
Thank you, Tathagat. Thanks for the kind introduction. I will start to share my screen. Mm, yeah, so, okay. I hope it's visible to everyone.
Yes, it is visible.
Yeah, so let me know if if you guys see any black spots on the screen because of the chat window or something else. So
No, it's perfect, Anurag. You can
thanks,
start.
thanks. Yeah. So thanks for the introduction again, Tathagat. I will be introducing the topic of domain adaptation with limited label data to everyone today. And yeah, we often hear about artificial intelligence breakthroughs, right? Like DeepMind had recently been able to solve a 30-year-old problem of protein prediction in biology, or Google released their recent image generation AI, which is Imagine, and it astounded everybody. Previous to that, OpenAI released DALL-E 2. So all these breakthroughs are great, but is AI all the breakthroughs, or are there any other dark underbellies of the AI that we need to address as researchers? So usually what happens is that a lot of times such news does not get the coverage that the hype gets, but current state of the art AI has a lot of limitations. For example, recently in one of the long form articles presented in New York Times, the journalists did an extensive research and reported that the Facebook had to apologize after their AI put primates label on videos of minorities in the US, more specifically the videos of black men. And although the company accepted it as an unacceptable error and they have been trying to mitigate, we need to go into much deeper reasons why such things happen. And there is a lot of realistic promise in self-driving research, about self-driving cars research, that they will get deployed soon. However, there were articles that say that nearly 400 crashes were reported by self-driving cars in US alone. uh, More recently, up until like as recent as like last month, what happened was that artificial intelligence was predicting patients race from their medical images. So this kind of differentially private data that should not be uh, something that the AI should be able to predict, or such sort of like protected data, is the data that the AI is being drawing conclusions on, or sometimes a lot of times spurious conclusions. And we have been just out of the pandemic, and we knew that in our last 2 years that there have been hundred of AI tools that have been deployed by medical AI research community that have claimed to build that have claimed to build been to catch COVID among the population. So they have the claims that they will be able to detect COVID in the scenarios in the wild. But honestly, none of them have helped. Some of them have been deployed, but most of them have fizzled out in terms of their accuracy in the wild. So using AI for pandemic did not really help. And on the similar trajectory to the fiasco in the Facebook, there was another issue with the Google's image labeling technology in AI. So they were again labeling the minorities in the images as gorillas. So Google actually fixed this racist algorithm by just removing the gorillas from their training set. These kind of fixes don't really help because uh, it is a lot of times that maybe some other confounding thing would look like some other minority, and they would be labeled as somebody else in a derogatory manner. So we have to go into the root of these things, and the root of these things is to be able to understand and solve generalization better. So according to recent research and acceptance about what generalization does encompass in the community, there have been three legs on which the generalization stands. So the first leg is about being able to adapt to new domains. So let's say your training data comes from a distribution which is from the real world images. Or your self-driving car is being trained on the roads in, let's say, Munich in Germany, and to test it, you deploy it to New Delhi in India. So the distribution of the roads is going to be much different. Or maybe another scenario could be that you have trained your model to be self-driving car during daylight images or in perfect weather conditions, but you test it out in rainy weather or maybe during nighttime. So how does our AI generalize to these new unseen domains and new distributions of the test? Then there is another caveat, which is learning with limited label data, or learning with limited data in general. So this is this at the heart of it. It has a long tail problem that suppose you have like number of examples on the y-axis and the class is on the x-axis, then you get this long tail distribution where you can see that this white region has very few number of images. So if you have such less amount of data for such large number of classes, they are obviously going to be misclassified. So how do you learn with like very limited number of examples given to you? As humans, we have this ability to be able to uh, generalize from few examples in quite robust manner. However, this still stands an open problem for machines. And the third part is about causal inference and reasoning. So consider this sentence like the higher the altitude of the city, the lower the average temperature. Here, the higher and the lower, which are the words that have been highlighted, define a sort of a relationship, but this relationship in terms of association to be inferred could go both ways. But however, we know that raising the temperature of a city will not increase its altitude. So there is this kind of like a causal relationship that exists only one way, that altitude is likely to cause lower average temperature, and lower average temperature may not have anything to do with altitude. So to infer these kind of causal inference and reasoning um, in machines is a much more harder task that humans are able to do because they are able to learn the underlying causal relationships and generalize. In this talk, however, I am going to focus more on the first two parts of generalization and the complex underlying relationship between both of them. So coming on to domain adaptation. So domain adaptation is, like I mentioned in the last slide, about adapting to new unseen domains. And for a typical ML pipeline, the let's say if you have been recruited as a machine learning engineer, and your task is to probably classify numbers or house numbers in the wild, or maybe like numbers on the traffic signs, then you would be asked to build a classifier, a digit classifier for that. So you go back and you collect some data. You collect data that has digits, and they come in various shapes and sizes, so you consider your data set to be very robust. And then you build your classifier using the most advanced machine learning algorithm that is out there. And then you follow all the good practices, like you hold out some test set from this training data, you hold out some validation set, you leave the rest of the data as the training data, you train a classifier on a training data, you tune your hyperparameters using the validation data, then you test on your test data, and you report a performance, and you believe that this should be the performance that is to be observed in the wild, because the learning theory tells us so. However, then you run your classifier in the wild, and your supervised learning setup terribly fails. And why is it so? Because in real world, often the IID assumption fails because we have finite training data sets. So the uh, observations that you had in the first slide about AI not being all about the breakthroughs is not because the algorithm researchers or scientists are connively trying to build a racist AI. It is more so because of the standard typical machine learning procedure, which allows us to only learn from finite training data. So in order to mitigate such challenges where new data comes from a different distribution, or from like somebody from a different country tries to test your face recognition software, then it is obviously an out of distribution example. How do you deal with such scenarios? So to solve these problems, we need domain adaptation. And yeah. So typical setting in the domain adaptation is to take a lot of target data from the distribution that you want to adapt to, and have its labels, and then combine all the training data from the uh, existing distribution and the new distribution, and train collectively on all of it, or more like some omission in case of Google. So in the original first slide example, we observed that Google removed its gorilla examples from the image labeling tech in order to refine their data set. So you could consider having labeled examples from new data as a refinement of your existing data, or expansion of your training data, and then you train and it's all good. But the challenging problem is that having such high quality annotated data from almost all distributions under the sun is not practically is not practical and not pragmatic either, because it has huge amount of labeling costs, annotation costs. It has also you have to deploy in multiple iterations. It is just not feasible. To like circumvent this issue, there has been an active research going on to have an interesting trade-off between the amount of label data that you have from the target. So let's say we have very few amount of labeled target data. Here, sketches are the target examples, the source are the real world examples, and then you have equally large amount of unlabeled target data from another domain, here sketches for the corresponding real world images. And then somehow using this label data, you want to also like leverage unlabeled data in order to improve the performance or adaptation performance of your model to this new domain. However, the key issue that researchers found out was that the semi-supervised domain adaptation needs label target data, which is manually annotated first. And second, that SSDA performance is very dependent on the choice of this label data. Like, had I given you some other example in this label data, let's suppose Eiffel Tower, is I give you the label of Eiffel Tower instead of the banana tree, then or maybe coconut tree, then what would happen is that the performance could drastically improve or decrease. We In this work that we did for CVPR 2021, we try to address this whole issue, that somehow if we could allow the machine learning model itself to tell us which data does it need to be labeled in the target. So yeah, so the motivation was to solve problem of selecting best samples to annotate. So let's say you have large amount of unlabeled target data. You select some diverse and informative samples from your unlabeled target data. You annotate them using some human annotator or some another machine learning based algorithm that is more powerful, and then you have the annotation. So for this figure you have the cell phone, and for this you have the palm tree, and once you have the annotated samples, then you can use them in your classification procedure in order to improve the performance. Yeah. So this brings us to another big question that we tried to solve was how are target samples chosen for labeling, which is a natural question that would come, that how are target samples chosen for labeling. For that, we need to understand that there are two important ideas and observations to make. So if we have this uh, different domains. Let's, for example, look at this observational figure. Let's suppose we have sketches and we have real images. So here you have sketch of a rabbit and a corresponding real world image of a rabbit. And you have sketch of an image and a corresponding real world image of a table. So the key observation here is that the sketch of a table does not actually differ a lot in terms of visual features from the real world image of a table. However, if you notice, the sketch of a rabbit actually differs quite a lot in terms of visual features and detail from the real world image of a rabbit. So for us, in the semantic sense, these two images in two different domains are equivalent. But for a classifier, there exists a lot of gap between the sketch image of a rabbit and a real world image of a rabbit versus sketch image of a table and a real world image of a table. So this is like the class-wise domain gap. So there is this first problem of class-wise domain gap. And the second problem is about the number of examples per se. So for that, I would take you to the second figure. So let's say we have this semantic space before domain adaptation, and the blue. So basically, the blue color represents the table class, and golden color represents the rabbit class, and the shapes correspond to different domains. So as you can notice, before the domain adaptation has been trained, like you have a classifier that has been trained on the real world images. So the classification of the squares is pretty good. However, the classification of the triangles is not that good, because the domain adaptation classifier has not been trained to classify the triangles properly, as it has been only trained to classify the squares in the most effective. But another key observation that translates from the observation into the semantic space is that you will notice that the blue class, which is corresponding to the table, the sketches and the real world images are very close to each other. And uh, in the corresponding space for the rabbit class, the sketches and the real world images are very far off. So we want to somehow be able to compute a measure that allows us for incorporating class-wise domain gap and imbalance. So another reason for the closure of this gap is that you can notice that there are a lot more examples for table suppose in our data set, than there are for like rabbits. So rabbits obviously become harder to train for, and then if they have even higher domain gap, then the situation only gets worse. So somehow in an ideal situation, what we would want is that the classifier looks like this, perfect, that it is able to classify the real world images also, and it is able to classify the sketches also. But if you notice, then the key observation to achieving such a classifier would be that we have a measure that allows us for incorporating the effect of class-wise domain gap and imbalance, so that we could have more examples labeled from this sketch of rabbits than from sketch of tables, because to adapt to sketches of tables, we don't need a lot of labeled examples. However, to adapt to sketch of rabbits, we need much more examples. It is more clear from this figure that if I have trained a classifier on real world images, then to classify this, I will not need many labeled examples from the class of sketches of tables, but I might need a lot more examples from this class, because the classifier to classify as rabbit has been fine-tuned to look for features in images like these. So it might be picking out features like ground and background and maybe vegetation in order to classify a rabbit in the first place. So in order to teach it to classify these semantically labeled sketches as rabbits, I have to give much more labeled examples. So another observation for that. So how do I give more examples for sketches of rabbits is again in the reason is in this figure. So if you notice, there is an idea called as the class prototypes. The class prototypes are nothing but the final layer weights of a classifier. So to classify the sketches of tables, the class prototypes might not need to move much from their original position. So this dotted star is the original position of the prototype. However, for the rabbit, since the semantic distance between the two, as shown in this figure, is much larger, the prototype movement is going to be higher. So this is the key measure that allows us to basically identify which of the classes actually need much more help in terms of the labeled examples for adaptation process. So this rate of adaptation of the class prototype or the class prototype movement is a good indicator of class-wise domain adaptation. So I mean, this is not the sole indicator that could be used. We are experimenting with a lot of different indicators, but our results for one of the methods that we publish shows that rate of adaptation for class prototype works. Yeah. So coming on to the method, the exact method that we use for calculating the prototype movement. So when we are training at different epochs, what we have is that we have the class prototype for a class C at iteration T, and we also store the same class prototype from like a previous epoch, let's say T minus one of the same class. So the subscript here shows that they both belong to the same class. So it's actually the final layer weight vector. So you could think of it as the row one. So we keep track of each row in the entire training epoch process. So then we compute the Euclidean distance between these two rows of the final layer weights. This gives us the distance that the prototype has moved during that epoch in the training. So we compute a moving average for the robustness of this metric. And then once we have a robust moving average for, let's say, last 1,000 epochs of training of our data, then what we do is that we have this distance that has been computed for all the class prototypes. So like I did for class superscript C, I do it for all the classes from 1 to C. And then I take the mean of all distances. So this is like my mean movement of prototypes across classes. So on average, prototype moves by this distance. And then what we do is that we create a class-wise uncertainty coefficient. So you could think of equivalently the class prototype movement as the classifier being more uncertain. So uh, the classifier would be less uncertain for table class, like in the previous slide, than it would be for the rabbit class, because sketches for rabbits look very different from the real world images of the rabbits. So we use a simple strategy to compute the coefficient, that if the coefficient, so if the distance moved by the prototype is more than the mean, then we have the ratio of the distance by the mean as the coefficient. And otherwise, for the classes that are relatively stable, we set the coefficient to 1. You can notice that this is like sort of the movement of the prototypes at different epochs. So at t is equal to 2500 epochs, we have calculated the average weighted prototype movement from 0 to 2500. So you can see like for a data set with, let's say, 127 classes, this is the profile of the average movement. So you can see that the sum of the classes are very uncertain, and they sort of remain uncertain consistently, uh, even despite supplying examples in between these epochs based on this classifier uncertainty. So what we do is that once we have computed the classifier prototype movement, we use it somehow intelligently. We use this coefficient to supply the labeled examples. I will cover that in more detail in the next slide. So once the uncertainty has been established, we also want our sample selection to be diverse, because let's say that your classifier is training, and you are quite uncertain about the rabbit class. So the classifier uncertainty coefficient for the rabbit is going to be very high. But if you have a labeling budget of, let's say, 100 images, and you supply all the labels from the rabbit class, then what it would mean is that effectively you have exhausted your labeling budget on the class which was most uncertain. But maybe the rabbit class could have adapted to a particular amount of accuracy after supplying only 10 examples. So at one point, there is some sort of diminishing return in supplying more labels, even for the classes that are very uncertain as well. So for that, we consider that there should be some amount of diversity also in the selection of examples. So then the diversity metric is computed using k-means clustering. So if we have like C classes, then we consider two C clusters using k-means. So we consider twice the number of cluster centroids as the classes, just to keep intra-class clusters into account. So once we have these 2C clusters using k-means, we have 2C unlabeled target examples nearest to the cluster centers. So once we have done the clustering, we will extract 2C examples as the cluster centroids, which are nearest to the cluster centers. And after we have got these 2C samples, we obtain the class prediction for each of these samples. So we forward pass this example through the model, and we obtain which class does it belong to. So we get the pseudo label for this class, and then after we have the pseudo label for this class, what we do is that we compute the final uncertainty distance of these examples using the so the pseudo label for this class is used to get the uncertainty coefficient corresponding to that class. So once we have the pseudo label, we can use the uncertainty coefficient that was computed previously, and we can then have this cosine similarity with the example of the prototype, and we can multiply these two to get final robust distance. So the diversity is considered using k-means, and the classification uncertainty is held as a coefficient that is multiplied to like increase or decrease the weight of the distance in the ranking list. So once we have computed this ranking list, we select top C samples, so the most diverse top C samples, and then we do this at particular time intervals, and we repeat until the labeling budget is exhausted. So we only select C examples at a time because of the fact that I mentioned previously that we would want to account for the fact of the diminishing return, because if a particular class is, let's say, uncertain, that we want to prioritize it. However, we don't want to put all our eggs in one basket, because if it would be the case that the classifier could become less uncertain even with lesser number of labeled examples, then we would want to intelligently exploit that trade-off. Okay. Going on to another part that we had to handle. So this was about like the class-wise domain gap that existed. But the another observation that we had made in our primer slide was that what if there is like a large number of examples for one particular class? So if there are large number of examples for one particular class, that would also impact the class prototype movement or the learning. So you can see that this is like one of the domain adaptation data set that we use. So we have the histogram for all the domains in the domain net data set. So this is the real domain distribution. This is the sketch domain distribution, painting domain, and clip art domain. So if you notice, if like a histogram has a large width, then it is highly imbalanced, because on y-axis we have number of classes, and then we have like on x-axis the number of examples. So if there is like a large range in which the number of examples exist in any of the classes, then the data set could be thought of as highly imbalanced. So these are the examples of a histogram which are highly imbalanced data sets. So an ideal data set like CFAR10 would have a histogram of number of examples at 5,000 and all the classes at 10. So you would just see a one single bar. However, for imbalanced data sets in the histogram perspective, you would see a wide distribution. So and to cater for this difference in the number of examples, we have the idea to weigh hard examples. So we weigh hard examples both in our source and in our target. So for the source, we use a version of focal loss, which is called as the class balance focal loss. So the class balance focal loss takes into account the number of examples in its coefficient. So this delta 1 is a parameter that is a hyperparameter to tune. However, NC is the number of examples in each class, C. And then you have this another coefficient, gamma 1, that is very similar to focal loss. So it just like sort of helps you more to put more emphasis on the uncertainty of your class prediction. So this is how we weigh the source examples for minority classes. And about the target example weights. So doing target example weighting is relatively harder, because for targets, we don't have label data. So now that we don't have labels, it's much more harder to know in the first place which classes are minority and which classes are majority. However, we try to figure it out using uncertainty. So we compute the uncertainty of the um, unlabeled target example by like forward passing it through the classifier, and then we obtain the probability that it belongs to a class C. So let's say if you have capital C number of classes and you have an unlabeled target example that has been denoted here by subscript UT, uh, you take the maximum prediction of that example and you subtract it from one, and then you get the amount of uncertainty that is present in the classification of that example. So we take this uncertainty, we do a linear transformation on it, piecewise linear transformation to be precise, and we get a coefficient. So we get a coefficient for this example, and then what we do is that we use this coefficient to do weighted entropy minimization. So you see the sum, this is nothing but entropy. So we do weighted entropy minimization. So we put more emphasis on the minimization of the entropy for the examples that are more uncertain. So that is why that is how we do target example weighting. And however, there is an underlying assumption, a caveat here that minority classes have to be more uncertain. So this in effect is also going to weigh examples from the majority that might be hard. That is why it is not exactly catering class imbalance, but weighting hard examples. However, in our experiments, we have found that weighing hard examples and taking care of the minorities are sort of like linked objectives. So doing one helps the another. Yeah. So with all this pieces together, we tie them up, and this is the entire bird eye view of our star algorithm. So this is the algorithm in its entirety that we propose. I'll go through each part of it to get you the complete idea of the process. So you can see the aqua lines. And the aqua semicircle or the oval is for denoting the labeled source. So it denotes the aqua color would denote the source, and the magenta color denotes the unlabeled target. So what we do is that we have this feature extractor or the classifier, the n minus one layers of the classifier, which are denoted as F. We feed the label source through F, and we get feature vectors. So I get feature vectors for the class one of source. I also get the feature vectors for class two of source similarly. And for the unlabeled target samples also, we could do the same thing. We could take the target example, we could feed it through the we could feed it through the n minus one layers of the network, and we can observe that we get some magenta color stars and triangles, which semantically represent the unlabeled target class one and class two. You can notice that there are black stars and black triangles. So the black triangles and black stars are used to represent the feature vectors of the target examples that are labeled. And then once we have these feature vectors, we can feed them through the final layer of the classifier, which is initialized with glow vectors. I will come on later to this part as to why we do this and why does this help. Then you see that the labeled source examples and the labeled target examples. Both of them are fed through the class balance focal laws. Uh, so this uses label data, and we feed the label source and label target in the class balance focal laws. For the unlabeled target, like I mentioned in the last slide, for weighing hard samples, we do uh, like weighted entropy minimization. So that is represented here. So as about to how these black examples are labeled in the first place. So originally we do not have any labeled target examples. What we do is that once we start to adapt in this representation space, once we start to train using the source, we compute the classifier adaptation uncertainty. So it means that we compute the beta coefficients that I had mentioned. And then we also compute a diverse sample selection. So we take all these target features, unlabeled target features, and we compute the diverse sample selection by the k-means procedure that I had mentioned. Then we combine these two and we select the most informative samples. So once we have selected the most informative samples, we can send these to an oracle. So an oracle will annotate these examples, let's say cell phone and cookie as cookie and cell phone for us. So we get the ground truth from the oracle for these examples, and then this label target is fed back again into the classifier. So this loop continues until the labeling budget is exhausted, and then we keep on training on the number of labeled examples that we have, and we train until convergence. So about the initialization with the glow vectors, so we do that in order to improve the semantic understanding of our semantic space. So we initialize with a 50 dimension glow vectors for, let's say, if we have labeled source examples. So we have, let's say, class rabbit and class table. So for class rabbit and table, we compute the glow feature vectors, 50 dimension glow feature vector for rabbit and for table, and we use them as rows in our final layer classifier matrix. So this helps in two ways. First is it improves the initialization, and also it improves the runtime of the algorithm, because once we have to compute the, because you remember, to compute the classifier adaptation uncertainty, we had to compute the Euclidean distance between the rows. So if the rows are, let's say, 50 dimensional instead of like 2000 or 4000 absurdly large dimension as observed in AlexNet or some VGGNet, then you get a significant gain in performance by reducing the dimension of the rows. Yeah. So about the more quantitative part of our work, what we did was that we tried to benchmark our performance on all existing data sets that were there for semi-supervised domain adaptation. Although our work does not like actually compete with the semi-supervised domain adaptation in terms of performance, because for semi-supervised domain adaptation they use labels from the start. However, we still show improvement on semi-supervised domain adaptation algorithms despite being different in task from them. So we consider three main data sets. So domain net data set, it has 4 domains, 126 classes, and they have some 7 domain adaptation scenarios. So maybe like from real to clip art, from painting to clip art, from sketch to painting. So for these 4 classes, you could have 4C2 domain adaptation scenarios, but they drop off the scenarios that are easier to like do. So training on, let's say, clip art images and then evaluating on real world images, somehow the features transfer easily. So that setting would be dropped. So only 7 hard and interesting domains adaptation scenarios are considered. For office home, so it consists about the things that are found in office, and so it consists about the things, the classes of the objects that are found in office and home. uh, we have 4 different domains and 65 classes and 12 domain adaptation scenarios. And we have like Office 31, which has 31 classes and 3 domain adaptation, 3 domains and 2 domain adaptation scenarios. Again, one of the domain adaptation scenarios is easier to implement, so it is dropped off, and only the hard and interesting domain adaptation scenarios are considered. Yeah. about the quantitative results. So we observed like all these methods are previous state-of-the-art methods that are in semi-supervised domain adaptation literature. Our method implicitly does not compete against them. However, we observe that we are able to beat these semi-supervised domain adaptation methods for domain net using ResNet 34 as a backbone, and on Office Home as AlexNet backbone, we are also able to beat the existing state-of-the-art methods. And some more quantitative results. So we found that we were able to beat most of the um, previous state-of-the-art methods on Office 31 backbone as well for both one-shot and three-shot scenarios. So these are the two interesting scenarios in Office 31 dataset that we consider. About the So here comes the more interesting part about the evaluation that we conducted. So there are three main components for our algorithm. So they act as the three main takeaway contributions. One is how to select uncertain samples or samples from the unlabeled target. So this is active selection or AS. And then is SI. So SI is semantic initialization that I mentioned, like how to initialize using glow vectors, the final layer. And then there is weighing hard target samples. So we consider different scenarios where we only take active selection, both of them and all three of them for actively labeled targets. And then there is a comparison with the manually labeled target. So we consider how well does our active label strategy compete against like a manual labeling strategy that has been the annotation that has been provided by like the dataset team. So the team that had released and open sourced their dataset, they had provided manual labeled targets for all the classes across different domains. So how does our active labeling strategy compete against the manual labeling strategy? We can see that we are able to improve the performance on almost all or quite a few scenarios as compared to manual labeling strategy. Yeah. And for further analysis, okay, so this is, I guess, repeat. So I'll focus on these two figures. Uh, yeah. So the table number two, it consists of like analysis of the class-wise average performance. So like I mentioned about the class imbalance. So the class-wise average performance is also that's something that we need to consider. So MME is basically a previous state-of-the-art method. So for the domain net data set in real world to sketches scenario where we have three shot. So three shot here basically means that we could get only three labeled examples per class and not more than that. So our labeling budget is only three labeled examples per class. And then how we compute the class-wise average performance is that we basically rank all the oops. So we basically rank all the examples in the classes based on the strength, the number of examples. And then we consider out of 126, we consider the lowest 30 minority and highest 30 majority classes. So that is how we compute the class-wise performance of the least number of examples present classes and the highest number of example present classes. As you can see that our algorithm performs much better overall, even for the lowest number of classes and for the highest number of classes. So this is the key takeaway, that we are able to improve the accuracy for the lowest classes. And this is the more of a visual analysis of what our algorithm does. So these are the TSNE plots. So basically A is a baseline. The baseline is like the MME baseline that we use. And we compute the TSNE plots for 10 different classes in the semantic embedding space, and you can see that there is like a lot of like overlap and misclassification that would happen because of this overlap in the embedding space. However, we are able to like relatively reduce the overlap between the examples using our method. So hence improving the performance. So yeah, the idea of this TSNE graph is to effectively show that because of less overlap, we are able to improve the performance. So yeah, I guess that is all. Thank you for your attention. And if you have any questions, please feel free to shoot them.
Thank you so much, Anurag, for a wonderful talk. So, people who are in the audience, if you have any question, please raise your hand using the reaction feature in Zoom, and then you can unmute yourself and then ask question to Anurag. Any questions from the audience? Hmm. Okay, I see two questions. Abhishek, please go ahead, unmute yourself and ask question.
The question, sir. So the question is that just one question: which type of norm are you using in the distance? Can you just go back to the distance slide?
Sorry, because of like maybe background noise, I am not able to hear you clearly. Tathagat, if possible, can you like uh,
Yeah, even I could not. Yeah, Abhishek, I could not also hear you. Could you please try once again, or maybe type your question in the chat?
Am I audible now?
Yeah,
yeah, yeah.
Okay. So my question was that which type of norm are you using in the distance formula? If you could
So
go back.
like I mentioned, it's Euclidean distance, so L2 norm is
Okay.
there. So since I am computing this in the if I had to compute the distance between the features, it would be or the raw examples, it would be much more different. But since we like, I will go back to the slides. Yeah. Uh, since I am computing the distance between the weights, it does not really matter to use a more complicated norm or to have an abulation on what kind of norm would help, because the semantic space is continuous, and the L2 norm simply works.
okay,
Okay.
so
Thank you, sir.
Yeah.
okay, Anish, please go ahead, unmute yourself and ask question.
Yeah, hello, am I audible?
Yes, Anish, please
Uh,
go ahead.
yeah, okay. So, Anurag, I just had one question. So you mentioned that in the star algorithm, you're taking the unlabeled target data, and after choosing a certain portion of them from the k-means clustering, you're then labeling them as well. So,
Yeah.
how many times do you need to repeat this process, or is there a limit to that?
So, I mean, it depends honestly on your labeling budget. If, in effect, you could use this idea to just label everything in your unlabeled target, but because of the pragmatic reasons, it is not possible. So, we have devised an order to rank in priority. If you have like fixed amount of resources, which one of them would you label first? So, this process would go on maybe C examples at a time up until your labeling budget exhausts itself.
Okay, okay, thank you.
However, like to add to this, I would like to mention in the comparison. So the comparison is fair in the sense that like all the SSDA algorithms, they let's say they use 100 examples from the beginning. So we restrict our labeling budget to 100 examples. So we would run this process only until 100 examples are labeled, and after that we have exhausted our labeling budget, so we would stop.
Okay, got it.
Yeah, thanks, Anurag. So I have some questions. Uh, so first of all, if I understood it, I have two questions basically. So one is let's start with the labeling budget. So is it some kind of hyperparameter that you choose, or you compute this labeling budget somehow?
I mean that is sort of like the more of the user-centric decision that you have. So if you want to label 100 examples, you can run the algorithm with 100 examples. However, when we run the algorithm to like compare, like I mentioned, I set the same amount of labeling budget that the semi-supervised algorithms
Hmm.
have. So here, one shot means one example per class. So then we compute if there are 126 classes, then my labeling budget is 126.
Okay, okay. And the next question is if I understood it correctly, you are iteratively labeling the unlabeled domain, unlabeled
Yeah,
examples, right? So I see quite a nice overlap with the concept of active learning, right? So could you
yeah.
please throw some light on
Yeah.
this
So
direction?
maybe I actually missed it in like explaining it, but the idea comes from the active learning for sample annotation.
Okay, so it's basically the active learning structure, right?
Yeah, so
Okay.
it's an active learning structure, but how do we do active learning? How to devise an active learning algorithm for semi-supervised domain adaptation
Hmm.
scenario? That is the research problem.
Okay. Yeah, thanks. I said two, but it seems I have now one more question. Just could you please go back to the last slide where you said some oracle or something like that?
Yeah,
Yes.
yeah.
So here, what is an oracle? Like,
So Oracle could be a human annotator or some other machine learning algorithm that provides you with a label of the example. But in the experiments that we conduct, we don't use some other machine learning algorithm. We get the ground truth for these examples from our data set.
okay, okay, yeah, that makes sense. That
Yeah.
makes sense. And I think in chat, someone asked that if they need to read more on this topic, if you have any resources you
So,
can share.
yeah, there is some resource with respect to the paper that we have in CVPR.
Hmm.
I can share the link with Tathagat for the paper, and basically from there you can look in the related work section, and you will have all the relevant papers in active learning and semi-supervised domain adaptation cited. You can like do a depth first search and then have all the literature that you want. So what I will do is that I will straight away share the link in the chat
Yeah,
with
that would be
the
nice, I guess, instead of sharing it with me. So you can put it in the chat and whoever interested can directly go to the
yeah.
link.
Okay. So yeah. So this is the link with the draft. And I will also share the link for the code so that if some of you want to play around, you can try to experiment with it, and you have a ready reference for the implementation as well.
Yep, that would really help the audience, I'd say. Thanks, Anurag.
Yeah, this is the link for the implementation. So yeah, feel free to like uh, basically shoot any questions offline if you have any doubts.
Okay, so thank you so much, Anurag, for take your time and giving us so interesting talk. I already see many people are commenting in the chat. That is quite interesting talk. And thank you so much, Anurag. And with Anurag, we started our Amygdala AI talk series, and maybe we'll be inviting more such young enthusiastic researchers in future. So please stay tuned with us. So with that, I would call it a day and enjoy rest of your evening or afternoon wherever you are in the world. So with that, I'll stop recording, and we can call it a day and we can leave the meeting. Right?